Okay, so we're going to explore a little bit more with two-dimensional motion, and so the previous video was a lot really fast, and so we're going to take a step back a little bit. Hopefully it wasn't too overwhelming, and we're going to look at some other scenarios where you might do some stuff with 2 dimensions. And so here we have some position vectors, okay, and so something you might notice is that I'm using the symbol R, okay, and before I get into the reason why, I just want to say with the equations we use, with some of the different types of notation and things like that, at the end of the day, I'm not really concerned about you using the same notation as me, because at the end of the day you can demonstrate you understand the topic without having to follow all the same exact rules. The rules are there for a reason, but if those rules don't make sense to you, I don't think it's a big deal to deviate from them. So what really matters is that you understand what you're doing, and so if you need to make something, change the way you do something so it makes a little more sense to you, that's fine. Okay, so anyway, these are position vectors, and the reason we use R here is because X is traditionally used for like horizontal and Y is traditionally used for vertical. Again, if you wanted to use X here, I'm okay with that, and oftentimes I will use X here, and like average velocity is going to be displacement over time. We can still use delta X for displacement as opposed to like delta R. Okay, I guess you could use either of those. So anyway, we have these 2 positions, and so there's some object that starts at position 1, and we'll say that 10 seconds later it's at position 2. Okay, and so our goal here is to find the displacement, delta R, or I don't even like writing that. I'm going to say delta X, and we also want to find the average velocity. Okay, so but before we do those things, I'm going to sketch a graph of it. Okay, and so R1 is negative 5i, so negative 5i plus 8j, so it's going to start somewhere like right here, and then it's going to end up at 7i plus 0j, and so we have this change in position. This is position 1 here, and that's position 2 here. It's going from there to there. So our displacement vector is going to look something like this. Okay, it's going to have some angle, and it's going to have some magnitude, and then we can also use that to find our average velocity. So displacement is going to be the change in the position, so that would be R2 minus R1, and so for I, that's going to be 7, and these are in meters, we'll say. So 7 meters minus negative 5 meters for I, R2 minus R1, plus for J, 0 meters minus 8 meters for J. Okay, and that's going to give us, here would be a positive 12 meters, sorry, that's displacement still, a positive 12 meters for I, and a negative 8 meters for J, and that's our displacement. Okay, and so when we get our average velocity, then all we have to do is we're taking this and we're using taking our displacement vector and doing basically scalar multiplication when we divide by the time. Okay, and so when we do this average velocity, as long as we have the displacement, it can be either in unit vector notation or the magnitude direction notation like you saw before. Okay, so what we'll go ahead and do here is we're just going to take each component and divide them by the time. Okay, just like that. And so we get an average velocity vector of 1.2 meters per second I minus 0.8 meters per second J. Okay, the last thing, we're going to actually take that average velocity and write it in magnitude direction notation. So I'll have you go ahead and do that real quick. Okay, so we get that the magnitude of the velocity using Pythagorean theorem, so we have length of 1.2, length of 0.8, magnitude would be 1.44 meters per second. So it went on an average speed, or average velocity of 1.44 meters per second, and its direction was 33.7 degrees. You could either say south of east, or I would also say here, you could say below positive x, since it's not clear what the directions are referencing. Okay, and then we use the inverse tangent here to find that angle. Okay, and so average velocity using vectors. Okay, so we're going to do this again, but we're actually going to do, and this, we'll just do this one time. This is actually three-dimensional vectors showing the position of an object in three-dimensional. So not only do we have the x and y plane, we also have the z plane right here. Okay, and the way we find displacement would be exactly the same. Okay, we're not going to graph it because it would, if I tried to graph it on here right now, it would be overwhelmingly confusing to understand because I'm just not good enough at drawing. But we can still find displacement by finding the change in each kind of dimension of it. Okay, and so we'll say r2 minus r1, so negative 4, and we'll say these are meters, minus 6 times I plus negative 1 minus negative 3, and these are again meters for j, and then we'll do the same for k. So 2 meters minus 6 meters for k. Alright, we simplify it all, and we get displacement equal to negative 10 meters I plus 2 meters j plus negative 4 meters k. So now we have this three-dimensional displacement vector, and if I were to ask you how far it traveled, like the magnitude of our displacement, we're not going to even bother with the direction, but to find the magnitude of this, we use the Pythagorean theorem again. Okay, and this is why I want to show this example. I think that this is pretty interesting. So we can still use the Pythagorean theorem in three dimensions, and the way we do that is we say the square root of negative 10 squared plus 2 squared plus negative 4 squared. Okay, in three dimensions it still works. So instead of being a squared plus b squared equals c squared, it'd be a squared plus b squared plus c squared equals d squared. Okay, and in fact it scales up to as many dimensions as you want to use. Okay, which is pretty cool. Now, I don't even know how you'd use it in 4 dimensions, but it'd be interesting to see. So anyway, we'll go ahead and calculate the magnitude here. Okay, so we'll say this gives us a displacement of about 11.0 meters. Okay, and there we go. Alright, so we have a problem here where we have a particle, starts at the origin, has initial velocity that's horizontal, it's got acceleration that's both horizontal and vertical. This one's asking how far it moves in the x direction before it turns around, and then to find the velocity at that time. So we saw something similar to this, but I want to practice again and just highlight a couple of things. So the first thing that I want to mention, so this is constant acceleration, which actually means that we can use kinematics, but we don't have to. We can. But whenever we're looking at stuff like this, it's helpful to separate it into two different kind of like sets of coordinates. Because everything that has to do with x, both position or displacement, we'll use displacement, initial velocity, final velocity, okay, all those things are specific to x, and we'll get rid of the subscripts there since they're on the side with x. Okay, so anyway, these things are specific to x, and acceleration for x, and then there's comparable things for y that are specific to y. And so when we're doing these, it's like you're doing two separate problems, because between the two of these, the value for acceleration doesn't relate to any of these. I can't use any of these x quantities with the y quantities, and I can't use any of these y quantities with the x quantities. And it's important to separate them, because basically two-dimensional motion is just two sets of one-dimensional motion. Okay, but there's one thing that does cross over, and that one thing is time. Because time is a scalar, it doesn't have direction. And so the thing that connects these two sets is time itself. Okay? And so in this problem we have a starting velocity here of 3 meters per second for x. For y, we have a starting velocity of 0 meters per second. We actually know, so it says, we'll get to that in a second. So we know that acceleration is negative 2 meters per second squared here, and it's 3 meters per second squared here. We don't know the final velocity, we don't know the displacement, we don't know displacement, we don't know the final velocity. Okay, so that's all the information we've been given. Then it says here, how far does the particle move in the x direction before turning around? And so this is a clue that tells us that it's turning around. And so we know something special happens when it turns around, and that is at this point right here the velocity is 0. So to solve this question we could actually say, okay, at that point velocity is 0. I can then use kinematics to find delta x and t. Okay, and then if I can find t, I can solve for velocity for y. Okay, so let's go ahead and do that. So to find delta x, I'll use this equation here. V squared equals v naught squared plus 2ax. Okay, so v squared equal to, so this is going to be 0 though, so we'll say 0 equals v naught squared, so 3 squared plus 2 times negative 2 times x. And so we solve this, 9 divided by 4, so displacement's going to be 2.25 meters. Okay, we can also use, we'll probably use this equation to find time. Okay, so v equals, 0 equals 3 meters per second plus negative 2 times t is meters per second squared. T is going to be equal to 1.5 seconds. We'll put the 1.5 seconds right here, and then we can take that and use it with this and with our initial velocity for y to find our velocity for y at that point. Okay, so I mean, I know that I went really fast through that, and the challenge here is just that we're taking what we've done already and doing it twice. And the thing that's confusing is that these things and these things just have to stay separate, and this thing can go back and forth. The time can go back and forth. Okay, and so this is why I like to encourage sometimes writing equations, because sometimes the functions can be helpful. So, well, real quick, go ahead and solve to find what would be the velocity for y at the point that it gets to that furthest horizontal position. So we know it takes 1.5 seconds to get there, so you can use that with the information over here to find the final velocity for y. So go ahead and do that. So we'll use this first equation, or yeah, I think this is the first one. Anyway, we'll use this equation. We plug in acceleration, we plug in time, initial velocity. We get this final velocity here. Okay, and so we can write even our velocity as a vector here. So this would be the velocity at the time that it reaches the furthest x position. Okay, and I wanted to talk about this because it's important, but that we're not going to really get to two-dimensional motion in this level. Most of the time when we have two-dimensional motion, the acceleration in one of the directions will be equal to 0, okay, which will make life a little bit easier for us. Okay, so anyway, we'll wrap up this video with that, and hopefully this is making some sense for you, and if not, then what really matters is in the next video when we start talking about projectiles. That's what's going to be the most important thing to take from this.